there's a lot of stuff that we've done with respect to like being able to define objective functions and like construct a regularization or construct like the problem that you want to optimize pretty flexibly, so that if you want to do a joint inversion or whatever, you can just like form your two data misfits, add them together, and do a joint. That's enough to do a joint inversion. And so I think that like pulling some of those pieces out, especially if they're not like, because in that case they're fairly simple, because all you need is a forward operator and then ways to get derivatives. So as long as those are exposed in a uniform fashion, then then it's pretty flexible. So that's sort of like one piece that we're thinking about there.
Okay, so this is the inversion stuff in Simpeg. It's in Simpeg right now, right?
Yeah. So this is, I can pull up the. There's sort of three relevant pieces, but the core of it is this objective function.
Okay. Objective
file.
function.py.
Yeah.
And so I remember looking at this some time ago, but not lately. So you're defining the add and multiplication by a scalar operators.
Yeah, and so because like you want to be able to throw an alpha or a beta or whatever on there, it needs to know like when to actually apply that. So looking at both then the data misfit and the regularization sort of show how this is inherited and used.
Are you on the Google Doc? Liam?
Okay, yeah.
I was just sort of writing out some very basic things of like types of.
Oh yeah, that's good.
But I think that's like the basic. I don't know if anyone's sharing their screen.
No, but I could.
Okay.
Yeah, so like when Tikhonov regularization is constructed, like all we do is just add together like the smallness, smoothness, all of those kinds of things.
It was very interesting when I first saw that. I did this exact same design for Fatiando, like that you have the data misfit and regularization, and you add them together with the regularization parameter multiplying. What I found with this is that it's nice for me, but it's not good to expose that to users, because it's very hard to document what regularization goes with what, and sometimes we have some weird inverse problems that we implement, and they have custom regularization functions, so they aren't generally applicable. It's like specific to that one problem. So actually documenting that you need to use that regularization and not this other one is not very simple. It becomes kind of confusing for users, and users generally don't care what the math looks like. They might not even know. But what I think would be, so my idea for the inversion package was to have something sort of like that, so that we can build the inversion however we want, but then the user would be exposed to a more to a Scikit-Learn like API, where you have a class with a predict method and a fit method. It can't be exactly like Scikit-Learn because they usually deal mostly with linear problems.
Yeah.
So that whole thing with a matrix and a vector doesn't really work for geophysics. But it can be similar where the class defines sort of the model, and then you give data only to the fit function or the fit method. And then it would estimate parameters, and you keep those parameters stored in a class attribute. And if you call predict and you give it also like coordinates or time or whatever, it should use the stored parameters to predict data. And the cool thing you can do with that is that you can sort of reuse a lot of the cross-validation machinery from Scikit-Learn. So then whatever goes on under the hood, it doesn't really matter what it looks like. Only people who know the math for the inverse problem would actually look at that. Right? So you could have these two layers. One that we provide, so we would know which regularization needs to go with whatever normalizing factors need to be applied, we can determine that for the user. But then since there is this lower level API, if they want to build something on top of that or customize the misfit or use some, try out some different regularization, they can still do it right through the low-level API.
Yeah, I really like that idea of having these two different libraries that are tackling sort of two different things, but are leveraging each other.
Yeah.
So that we have this low-level API that, because I think sort of where some of the differences are with the SimPeg audience and the Fatiando audience are where like the primary users of SimPeg are people who are looking into and researching inversion algorithms. And so in that case, like what we want is a lot of flexibility at the objective function composition level, and even like overriding things like the beta parameter isn't a float. Now it's something that changes through the sort of inversion process. And maybe you're flipping between two data misfits and regularizing your DC data misfit and then your fluid flow data misfits, and like then putting up the regularization parameter. And so like those are the type of things that aren't ever really going to be exposed at sort of the at like a Scikit-Learn type interface, which is the interface that is actually going to be broadly applicable. So I think they can be quite, like those two things can be hugely complementary.
Oh yeah.
What are your thoughts on setting up the forward simulation in this sense? Because like you still sort of need user input to design a reasonable mesh. There's steps of that and maybe pieces that can be automated, but there's still an iteration with the user there. How do you?
Yeah. So for example, if you're doing a there could be two approaches to this, like the inversion class or the estimator class. It could ask for an entire, for like a pre-built mesh. So the user would define the mesh and pass it to the class. Or it could also ask for input parameters like the boundaries of the mesh or whatever, and then build the mesh inside the class. It's usually better if you ask for the mesh class.
Yeah.
Instead of trying to instantiate it yourself. But so with keeping this, like the estimator is not really storing the data, so it's kind of representing the mesh or the model that you're fitting to data. So it would receive mesh parameters and regularization parameters and all that, and so that is stored in the class. And when you call fit, it would estimate parameters, and you could insert those into the mesh. as well. So if the user wants to plot it, there could be like a object dot mesh or dot whatever that contains the actual mesh with the estimated parameters.
Mm-hmm.
Does that answer the question, or?
Yeah, I think so. So I mean, like, we would prefer that users input that, but if not, we'll take a crack at it and maybe print some useful outputs and things like that, or like, yeah, lean them towards a workflow where they at least go in and themselves sort of validate the mesh. Yeah.
Because if you're at the point where you're kind of trying to figure out what works and what doesn't work, you really do want all the flexibility that Rowan was talking about, where like, you're not sure what kind of regularization you should use, or what kind of normalization makes more sense for this particular case. But usually once the paper is published, you kind of settled on something, right?
Yeah.
And
Maybe.
for the particular cases that you tested, right, it usually works. So when you reach that point, it would be better for users if you wrap that up in a class that contains all of that, right? So you could have like a class that runs this particular inversion with this particular regularization, and when you're using this kind of data with this kind of regularization, it's better to normalize the misfit by some factor, or you should do the forward operator, or sometimes there's some approximation for the Jacobian or something that you want to use.
Yeah.
So those could be built in. So you can have several classes that run sort of similar inversions. They're all going to be doing similar things on the back end, but they I sort of represent different methodologies, so that the user has less choice, which is not always a bad thing.
Yeah. Now, the Scikit-Learn API, I need to take a more serious look to get my head around that. The one thing we're doing in Simpeg, one thing we're doing in Simpeg right now is we're refactoring the way we do the forward simulation. And sort of looking forward, I think there's some interesting pieces there, because we're taking advantage of the properties library that Franklin and Rowan have done a lot of work on. So there's a lot of, like, it's nice, I mean, because it does auto documentation. It also does validation and things like that. So going in and, if we're setting up a frequency domain EM simulation and we want to make sure that the users define sufficient padding, we can go in and validate before we perform anything and basically say, like, does the mesh extend far enough based on the frequencies you've defined? Because sometimes, like, depending on the order of operations of how they set things up, like if they first, provide the mesh and then decide what frequencies they're going to use, there's sometimes an incompatibility there. So I could see some of those learnings translating quite nicely to the inversion side of things. We have all the defaults in place, and then have some sanity checks in there to say, not necessarily like prevent the user from doing certain things, but to say, like, hey, this is a bad idea. Just be aware that it's a bad idea. And yeah, so there's potentially some things there.
Yeah, I've been keeping an eye on properties. I like it a lot better than traitlets. The traitlets library is kind of weird, and it seems that the documentation is written for someone who already knows how to use it.
Yeah.
Yeah, properties sounds really nice. I think it would fit well with any, like, with the inversion and all the mesh and stuff. So looking forward to using that.
I think my sort of favorite thing about that versus traitlets is if you do like a dot tab on any traitlets model, it gives you about 17 things when you put like one piece in there. And like what we were trying to do is keep that namespace really clean. And so there's a validate and a serialize, and those are the only two things ever that it's going to give you, plus the properties that you've defined.
Yeah, that's good. It's not nice when you have a whole bunch of public methods that don't really need to be there.
Yeah, exactly.
And the serialization piece is nice for saving, like saving your objects and saving the state of whatever it is you've done. So.
So you were, Lindsay, you were mentioning the Scikit-Learn sort of interface.
Yeah.
I can share my screen
here.
Sure. Okay, is that working?
Yes, I think so.
Okay. So I was doing some experimentation with that, and just to see what could be done and what would work. So I was trying out just some basic linear models. Right, so this was a polynomial regression that I was running with some of the prototype code. So I have here the data points are the blue dots with error bars, and the dotted line is the true function. So the way I thought of implementing this is that if you're making something that's going to be user-facing, you would define a class. Ideally, it would inherit from something that might help define, like if you don't give me a Jacobian matrix, it'll auto-compute with some finite difference approximation or something. But so the methods that you need to define are pretty much what Scikit-Learn expects, which would be a predict method that, in our case, it can't really just take a matrix. Because if you're running nonlinear problems or whatever else, you don't have a feature matrix, right? Or if you're running a potential field inversion, you're going to have XYZ coordinates instead of the Jacobian matrix, right? So in my case here, it just takes the X variable and then calculates the Jacobian and multiplies by the stored parameters. And the Jacobian is just a linear, a polynomial fit Jacobian, X raised to the power of something. So then I would define also the fit method, which takes the auxiliary variable and the data, and it can also be weighted. And inside the fit method is where I'm using this linear misfit class and defining regularization as also a class. And this is where the
objective function piece.
Exactly. So making an objective function by adding these things together, it could fit in here. So instead of having misfit be a linear misfit that takes some parameters and then also takes the regularization, I could have a linear misfit plus the regularization parameter, which is defined in self.damping. I could have self.damping times damping added here. And then these misfit classes, they have a minimize method, which does the optimization. In case of the linear function, it just solves the system and spits back a parameter vector, which I use then for other things. So to use this, I could define the class and give it the polynomial degree and then call fit. And since fit also returns self, like in Scikit-Learn. So the main difference with Scikit-Learn is the arguments that it takes. So I'm taking here 2 vectors, or if it's a 3D inversion, it would usually take X, Y, Z and some data.
What are those? Those are the locations and the data value? Is that
yeah, these are the locations and data values for this. So it's an X and Y value for this polynomial function, for this sample data that I made. Right, so I just defined some test data here, which is like an X value and some measured Y with uncertainties. And I put in an outlier here just in case, just to see what happens. Because I was testing out some other stuff as well, and I wanted to see if the weights work properly. So in this case, I could also, I have built into the linear misfit that it can take a weights vector or a matrix, and it'll use all of that. So I can give it the weights, which would be 1 over error squared, and it'll fit. It can be used for a robust fit as well, where you could call this fit multiple times. But then regarding using the Scikit-Learn stuff, is that they have these methods where they define, so they'll have a regression and then they have a regression cross-validated, where it takes pretty much the same arguments, but instead of taking a single value for the degree, it would take like several values of degrees. And when you call fit, it's gonna cross-validate between all those values, and then it estimates the parameter and the best degree.
Okay.
It does all that in a single call. So what I have here is that I'm subclassing from the polynomial regression. And so I don't need to define the Jacobian and predict methods again, but this time my fit, it's running the k-fold cross-validation from Scikit-Learn. So I'm fitting a polynomial regression for every single degree that I give the function, and doing this across the folds, computing mean square error for which is for a cross-validation metric, and then choosing the smallest mean square error for and getting the best degree out of that, and then I call fit again, but this time using the degree that I chose. So if I want to run the cross-validated regression, I just run it instead of giving it a single degree, I give it a list of degrees from 1 to 14. And I'm just specifying a random state here so that the results don't change, but calling fit the same way that I would with the non-cross-validated class. And in the end, it gives me the estimated degree, which was 7 for this case, and I have a nice polynomial fit with the best cross-validated degree. This also works for multiple multiple hyperparameters. So for if you're doing a inversion, you could use this for the regularization parameter. And it works pretty well. This is the k-fold cross-validation is very robust. It does involve running several inversions, but when you're choosing the regularization parameter, you're going to do that anyway. Whether you do it manually or you're building an L curve or you're doing this, you're going to run it multiple times anyway.
Yeah.
Right. So I like this higher level interface. For that you can, it's easier to use, I think, for users, and since it's similar to something that is very popular like Scikit-Learn, the chance that someone already saw this interface before is big, so that's less work for us in documenting. But whatever runs under the hood here, with regards to how we build the misfit or how you build the objective function and how you solve it, that's pretty flexible, and it doesn't really matter for this high-level interface, right? Whatever goes on underneath. So this could look like something that this part could look like something that we want it to look, so that it looks like the math. So you can have the define the add and multiply parameters and operators, and that would be a nice way to use it.
In terms of your the self.misfit.minimize, is that using, or what is that using under that?
So so this is the minimize method. So It's
This is just a linear solver.
Yeah,
in this case.
and in this case, it's a linear solver, which is defined here. So it's something that takes the goal function. So the misfit, it defines a Hessian and a gradient, and I think a value as well. Yeah. So the misfit defines a Hessian and a gradient. So it knows how to calculate the misfit gradient, which would be the Jacobian, or is it Jacobian transpose times weights times the residuals. So it knows how to calculate all of that. And these solvers are functions that would take they take a function that calculates the gradient, a function that calculates the Hessian, and it could do like a Gauss-Newton or a Levenberg-Marquardt, or if you don't want to give it the Hessian, then it's going to do a quasi-Newton approximation or something. That all could be implemented in there. But yeah, so this could be, because I know in Simpeg you're doing a lot of adjoint stuff, right?
Yeah.
Yeah.
Yeah, and so I think from that side of things, like how we could go about that is have instead of having the misfit dot minimize, have the misfit be something that we could put into SciPy optimize potentially. Yeah. And so instead of having it hang off there, just be a function that you then pass the minimize to. So
Or
and
pass
then
the misfit too.
Yeah, sorry. And then there are a couple other, I guess, complications on our side in terms of like memory management that we have to be a little bit more prescriptive about, like when things get solved, which I think really are just details at that point, but important ones.
Yeah, a problem I had with the with doing the operator overloading stuff was that the code was very hard to manage, because it ends up using some not necessarily black magic, but it's some it's more advanced Python than just doing normal classes and functions. So the trouble I had with that is that no one else would touch that code.
Oh yeah.
So it became kind of hard to maintain. That's why I sort of try to get away from that. It's nice to use, but it's not necessarily pleasant to implement, because you got to keep track of order of operations, and then all of a sudden you're creating objects through addition, and then you're not sure what gets copied and what didn't get copied, and what's being copied, but it's only a reference, so that sometimes it's changing something else some other place in the code, and you forgot to make a deep copy instead of a shallow copy. So I was running into all sorts of problems with that. That's why I kind of decided that it wasn't worth my time to just so that I could have it look like the equation. And you can get something as flexible as that, but just without the operator overloading, and that makes it simpler. Simpler to maintain, not necessarily simpler to use. But I haven't looked at your implementation of all that. It's probably better than mine, because mine was very rushed and not very well thought out.
Yeah, and I think also that we have a couple of people who are like at least maybe 3 or 4 more people who would jump into that sort of level of implementation, and that means that it gets I like the load is shared a little bit more evenly.
Yeah.
And I think that also is could also just be a difference between the audiences that are like using
Yeah, for
this,
sure.
because a lot of times people are actually subclassing those things. And so if that makes sense, like they're actually interested in creating a new regularization objective function piece. And so that's like what their 3 years is about at like doing a PhD is like writing that thing.
Yeah.
So I think we can get some people jumping in there.
Yeah, because the people in Rio who are doing a lot of this, so it's like Valeria's students, they are usually they're it's kind of the same thing. Their PhDs involves writing some different sort of inversion, and sometimes that means creating some weird objective function. But they aren't expert coders, so they have a hard time jumping into that. They're usually learning Python at the same time that they're learning all of this.
Yeah.
So then if they usually end up starting somewhere lower level instead of just requiring them to already jump into, okay, this is the add method and this is how all the magic happens in Python. They get a little bit frustrated with all that.
Yeah,
that's fair. Too, and I think that's something that we need to do a better job of with a lot of this that is done in Simpeg is documenting like how to actually inherit a piece and build a new objective function and things like that. Right now, we're really lacking on that because I think like overwriting the add and the mul and whatever, like people don't actually need to know that that's happening. They just need to know what the result of that is and like to know which knobs you need to be playing with. So that's something, that we definitely need to do some work on.
And I think the splitting it out is sort of when that happens, and especially if other libraries are going to be dependent on it, then it needs to be better than it is.
Yeah.
And like have Leo, you go through it, and like us actually talk about, is it deriv 2 or gradient Hessian and stuff like that, so that we're sort of standardizing language on, so that people can jump between these various codes.
Yeah. No, that would be great, because I mean, I'm sure if we look at the Facendo code, it's gonna look extremely similar to this. I'm just looking at your add function here, and you're doing the same thing as I was doing. So like, check if I didn't have the zeros thing, which I like, in case you want to have like a default 0 regularization. That's cool. But I was doing the same thing, like, check what the class type is, and then when you add, you make this combo objective function, and then you give it the objective function lists. And multipliers. I was doing exactly, the code is very, very similar. Let me see if I can find it. I don't remember anymore what is in the master branch. But it's something very similar. I think that's in base. So this is my add function. So I'm making a multi-objective thing, but one thing that I was worrying about is that I gotta kind of copy the objects. Otherwise, say the person creates a misfit and then creates a regularization and then creates a goal that's misfit plus regularization. If they change the misfit instance, that shouldn't change the combined function.
That's a question.
That's totally a question.
If they're instantiating the misfit and regularization on the same line that they're attributing it to the goal function variable, so there's no variable storing the misfit. that's fine. But if there is, and then they change some parameter in the misfit, it would be weird if that goal function that is somewhere else doing something completely different now, if that gets changed, right? Kind of secretly under the hood, and they don't realize it. And so that's where I started running into problems with this. These problems started creeping up as I started using these things.
Yeah, I mean, from our perspective, that's like, so one of the inversion sort of schemes that we use is like a cooling beta, so that as the inversion is progressing through, you have some sort of directive that says, okay, this iteration, cool the beta. Like it's checking the global progress and then fiddling with the objective function.
Yeah.
And so in that case, the beta, that your multiplier, doesn't have to be a float. It just acts like a float and can be manipulated externally.
Okay.
And so like you actually want it to be a pointer in that case, and you're fiddling with it at the inversion level, at the global level, and you're changing your objective function.
So your optimizers are aware that they're dealing with a composite objective function.
Yeah.
Not specifically. It's that there's this list of directives, is what we call them, that just gets called at the end of every iteration of the global inversion that can do whatever it needs to do. So in that case, maybe reduce the beta value or choose a new beta, or it ups the regularization or something.
But the optimizer doesn't need to know that.
No, it doesn't.
Okay.
Yeah.
So okay.
You just need a hook at the end of every optimization step.
Yeah.
Yeah.
And another example of that might speak to this too is when we're using sparse norms, you have to actually go in, because we're using iteratively reweighted least squares, you have to actually go in and update the regularization at every step. And so that's another case where you actually do want like a hook to your regularization, and you don't actually care about your data misfit in that case. So we do want to actually be able to individually manipulate that.
Yeah. Okay.
So I have to go in a few minutes. I wonder what we want the. I think these conversations are extremely productive.
Yeah.
And even like as it sounds like Leo, you have on your sort of open source roadmap at least, and maybe that amount of time, the idea of pulling some of Fadiando apart.
Yeah, that's the main idea.
Okay.
Because I don't like the way it is right now. Because there's a lot of code that's something that I wrote for a class 8 years ago, and no one's touched it ever since. And it's just sitting there untested, and I have no idea if it still works.
Yeah.
And so I wanted to clean all that stuff out and get rid of Python 2 altogether, because I tried making a version that works in both. It's just a huge pain testing in both all the time.
Yeah.
So I figured it's 2018.
It's time.
It's time. It's going to be gone in 2 years. There's no point investing in something that's going to be gone in 2 years.
Yeah,
that's cool.
We might as well just ditch it altogether. And now with all the content environments and everything, it doesn't really matter. It's not hard to use Python 3 in one project and Python 2 in another.
Yeah.
Right. So I figure, okay, whatever. I'll just release whatever is in master right now, and then the next release is gonna be Python 3 only. And yeah.
What's your sort of timeline, do you think? Or like rough?
I don't know. So my current research is gonna require the inversion package and the gridding package. So that's kind of what I'm gonna focus on for the moment.
Okay.
And yeah, because I've been working on interpolation methods and sort of equivalent layer stuff. And that's where this interpolation package would come in. So I'm going to be focusing more on that. I was starting with the inversion package and kind of testing out some implementations to see what works, what doesn't work, and what do I actually want it to do. Try to define the objectives first, and then try to think of the implementation. But this was good, seeing the kind of requirements that you have in Simpag. It would be great if we could coordinate on this. Would you be willing to sort of try to develop a joint, like a multidisciplinary inversion package? Because it seems like I like the operator overloading stuff. I just don't want to develop it. If it's going to be just me coding that, then I'd rather not mess with it. But you guys have a larger team and more well-prepared developers, it seems.
Well, and I think also if we join forces, there's like a good chance that we could get the PyGimli folks to jump on board as well.
So from my chat with Florian at AGU, they mostly do Gauss-Newton type inversions, and their inversion stuff seems very similar. So they're also defining a method to calculate the Jacobian, a method to calculate predicted data, and then giving that to a general purpose thing that runs the optimization. Right, so it's pretty much the same design that we've been working on and that Simpag is using. So it seems like all three projects kind of converged on a very similar design independently.
And Dieter has been working. I've been working a bit with him to plug in EM-PyMod into Simpag. So that's actually helped us to generalize our forward simulation framework a bit, so that you can plug in whatever forward model you want to the inversion machinery. So I completely agree that like having all of these things, all of these different projects, at least coordinating at some level. And it's like having a higher level API, I think, would be a very good thing for usage for all of our packages.
Yeah, because one of the things that they do in PyGimli is that if you don't define a Jacobian calculator, they do the automatic differentiation, like with finite differences for you. So that would be a utility to live in in this higher level estimator class. Right? Like if you don't give me a Jacobian, there is one provided for you.
The
main difficulty will be kind of ripping out the assumptions of each library from the inversion package. So making it truly agnostic to the forward solver. So being something, okay, it's a function, and I give you some auxiliary variables and a parameter vector, and you spit me out a data vector. And whatever goes on in there, if you're running Fatiando code, if you're running PyGimli code, if you're running Simpag code, it shouldn't matter to the inversion. Whatever is going on inside of the predicted data and the derivative classes, the derivative functions. So, being careful to make that agnostic, I think it's just a matter of looking at the code, right, and seeing what we can strip out.
Cool. Okay, so is this, like, can we have maybe, I know, like, Lindsay's finishing up her PhD at the moment, and explicitly said to me before this call that she had zero time to take on any new projects.
But I still want to keep in the loop. I
wonder if, like, maybe I can do a rip out of the objective function side of things for Leo, you to take a hit at. And then maybe you put your the inversion sort of sketch somewhere, and we can see if we can start iterating between those two.
Yeah, that would be good.
And maybe I can start to compile some, and I think this is, maybe Lindsay has time for this, in terms of compiling thoughts on the design and constraints.
Yeah.
On sort of what, like, just looking through the code and the implementation, there were a number of thoughts that I've had that I need to like actually give a full breakdown on.
I mean, I don't have a whole lot of time for this as well. I mean, this is all on the side.
Yeah.
But so I can move the code to the Open Geophysics organization.
So is that something that you're?
Oh yeah, that's totally fine.
Okay.
I mean, if it's gonna be shared, it doesn't make sense that it's being hosted in Fatiando or Simpeg or whatever. If it's gonna be shared, it's better if it's somewhere that's also shared. What was I gonna say? Right, but it would be good if we could come up before doing a lot of coding, like try to come up with a list of goals and prerequisites that this needs to fit.
Yeah.
Right, so for example, you're doing a lot of stuff with the joint inversion, so just being Gauss-Newton is not good enough. And you mentioned that you need special hooks to be called during the optimization process, which is something that I never used that, so I didn't even think about it. So establishing those prerequisites would be good. So for my case, a lot of times some of the inversion methods are kind of weird and they're not really doing a traditional optimization.
Mm-hmm.
So being flexible enough that it could handle that as well, so that not assuming that every model is going to be run through the same kind of process is it's good to have. So maybe we can make wiki pages, right, in the on GitHub repos.
Yeah, or even just like a read the docs style thing, and just actually make the documentation first.
Yeah, exactly. So that's what I thought. Yep. Trying to come up with how we want to use it, and for example, try implement an inversion using the library before we actually code the library, and then we code the library that makes the inversion run.
Yeah, no, that sounds really good.
That sounds very good.
Okay, so I'll move the stuff I have to the Open Geophysics org, and then we can sort of start from there. I think I already have docs building on Travis CI and deploying automatically and all that. So that would, then we can start working on the docs.
Yeah.
That sounds good, Leo. I'll make sure that you're an admin in that organization as well.
Okay. Yeah.
It also needs a logo if you have other free time.
Yeah, sometimes I think I spend way too much time thinking about logos.
Yeah.
Well, the Fatiando logo is beautiful, so it shows.
Really
Yeah, I spend way too much time on that, but yeah, it's fun. It's relaxation time.
Yeah.
Exactly.
Oh yeah, a brief thing that I wanted to mention is that I've been breaking up a lot of my educational material stuff, like all the Jupyter notebooks that I was using in my classes.
Oh yeah.
So I've been trying to update those and sort of decouple them from my course so that they're standalone modules. And I mean, as always, like as proof that I spent way too much time on that, I made this organization. I had this organization for several years now. It's I called it the Geophysics Library. So I'm posting. There's only one repo there, and it's not done. But I'm gonna be putting the repositories there. There's a link here in the Google Docs.
Oh, perfect.
This is the magnetic anomaly.
Yeah, that's so a lot of my classes. I made these notebooks with widgets, and they're using some Fatiano code for simulation.
Oh, that's sweet.
So the magnetic anomaly, it was my attempt at explaining why the magnetic anomaly looks the way it does to the students, because they had a hard time picturing it, and I had a really hard time drawing it, like the standard drawing of a magnetized sphere, and then it disturbs the geomagnetic field in this way, so the anomaly looks like this.
Yeah.
Right, with all the here it's the vectors are in opposite directions, so it's going to be smaller. So drawing that in the blackboard was super difficult. So I made this notebook that calculates the induced field of a sphere.
Oh,
so you
cool.
have you can see a cross section with the vectors, and then I add a geomagnetic field to that, and so you can see where the vectors become smaller or larger, and they can use widgets to change the inclination and susceptibility.
Are you aware of the GeoSci work?
Yes.
Because I think some of that has quite a few. Again, your logo is way better than ours.
Exactly.
XYZ, right?
Actually, I like the one for the EM one. That's
which one?
The EM library. It's actually.
Oh yeah. With a dipole.
Yeah. Like that was nice.
Yeah, that's a really good logo. So what I like about the GeoSci stuff is that you have like a full text with like all the equations and all the derivations and all that. But what I wanted was like short individual modules that someone could use on their own course.
Yeah.
So say I'm teaching a GeoSci course and then I'm having trouble explaining the magnetic anomaly. You could just load up this one module, which is like a single notebook with a bit of text and an interactive widgets, graphics kind of thing.
One thing that, sorry, go ahead.
Yeah, no.
One thing that we could do, so we do have a page, I'll just send it through on Slack. Like Dom has developed some widgets for Mag as well. One thing that we could think about doing is like even just having either a separate module or maybe in the same place as something like the GPG, because it's targeted at sort of like intro undergrad geophysics, just having a collection at the end of notebooks and like what they're achieving, maybe a screenshot, and just like to be able to point to all of these things, because there's a ton out there. Yeah.
And so this is fun, and I would love to use Simpeg for some of the simulation stuff, because I coded up some finite difference wave propagation stuff, which I was using in the seismology and seismic classes. But it's nowhere near as fancy as the stuff we can do in Simpeg. But it's convenient because like you can the students could run the simulation, and I made an animate method that would like run the animation, make an MP4 and embed it in the notebook. So they could change some part of the simulation and then immediately have the animation there where they can run it. That's very unstable code. The animation stuff breaks all the time, and I can't get it to run on Binder. It's some FFmpeg issue. I don't know. It's it's weird. I've been trying to fix that, but I get not even an hour a week to work on this. But yeah. So I just wanted to point to this. So if you guys have any like small notebooks or something that, or anything like that that you would want to, I don't know, that you want to share? Or I don't know if it's all, I know that in GeoSci you have a lot of these notebook apps, and are they all hosted with the Sphinx docs?
No, not right now. That's on the list of things to do.
Okay.
There's links in the Sphinx docs like to Azure, which has all of them.
Yeah.
So yeah, there are connections there, but it would be nice to actually, what I would like to do is sort of build even just a static version with then the link up top, just so people can see like what the notebooks look like.
Yeah.
So. Yeah,
that's one thing I was struggling with is how to make it easy for people to reuse. Because having them install Anaconda and all this stuff, it's a bit of a barrier.
Yeah.
Especially on university computers where sometimes people can't really install stuff.
Yeah.
But yeah, Binder sort of works. It's a lot better now. I'm not sure from your experience with Azure, it seems that it works a lot better.
Azure's a little more reliable. So what they're doing with Binder is they've got, I think it's something like a few grand each month dedicated to compute power. And so they like open that up, and as soon as it runs out, that's it. So Binder right now is very much like an experiment to just see how well it's used and how quickly it's adopted. Azure, they actually sort of have a trajectory like to get people to start paying Microsoft. So in the sense that like if you need more compute power or you want stuff to be private, they have a track for that. So there is actually a lot more motivation for them to maintain the open source and like the freely available side of things.
Okay.
So far we haven't run into too many issues with it. As we've traveled around, it's been reasonably reliable. So.
Okay. Yeah, I'll try to get it running there. I mean, it's probably not a whole lot of work to make it run in both, right?
No, it's not too bad.
Okay.
Cool.
Okay, is there anything else? I know Rowan is busy.
Running off.
Trying to get out.
No, well, this is more. Oh, I shouldn't say it. We're recording. Yeah, no, this is good. Yeah, so I'll try and do some work maybe this weekend of even sketching up some docs on the objective function side of things, because I think that and the mappings piece could be easy to be pulled out of Simpeg and also cleaned up and sort of used by some of these higher level interfaces on inversions and regular inversions. Cool.
Yeah.
Do you guys want to plan to like meet next week even for just half an hour and touch base on where we're at? Would that be useful, or do you want to sort of have these as we make progress? I don't know.
I know that might be good.
Yeah, let's do next week.
Okay. Does this time work for you guys?
Yeah.
Okay, perfect. That sounds good.
Okay, so Tuesday morning, same time?
That works for me.
I'll send it a calendar right now.
Okay,
perfect. Thanks, Ron.
Cool. No, I'm super stoked to get some of these things and just us pointed at the same things, because there's like the educational aspect, the research aspect, and like getting sort of the momentum from these two communities into one place. And like Lindsay's is getting a lot of headway pushing to Colorado School of Mines right now as well as a couple other places in the States. So, and it's going to be in Berkeley in no time flat.
Yeah.
So I think it's like a good time to sort of just define what this ecosystem looks like and how we want it to be. And then it'll just sort of happen, right?
So. Yeah.
Exactly.
I think the biggest barrier is kind of defining what we need.
Yeah.
That was my problem with adopting discretized. Like, it got me thinking of, okay, what do I actually need from these classes and stuff? And I couldn't answer that easily. So.
Yeah, no, that's very fair.
Cool. Alrighty.
All right.
Yeah, so we'll talk next week. I'll try and get to some of this stuff on the weekend.
Yep.
That sounds good.
Okay. Don't work too much.
No. All right. I'll talk to you guys soon.
Yeah.
Thanks.
Okay. That was good. See ya.